Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. This is one way you can keep me going, inspired and refreshed. So here is a problem on structural analysis with which is statically indeterminate to the first degree. And I presented 12 different solutions to this so that that's one way you can master structural analysis, especially the methods of analyzing indeterminate structures such as beams. And the first one is the method of consistent deformations, combination of double integration method. So here is the given problem. If you look at the figure and evaluate, it is really statically indeterminate to the first degree. So the first step is we select the redundant, which is the reaction at B first, although it is RA that is required. Then after removing that, the beam will deflect and becomes determinate. From different basic methods on computing deflections, we can compute the deflection under B. Then in the second part, we apply a unit upward load and the corresponding deflection above B is denoted by FBB, and FBB is called flexibility coefficient. Finally, flexibility coefficient times reaction at B plus the deformation at B when support B is removed must be equal to 0. And from there, we can solve for RB. After solving for RB, we consider the entire system. We sum up moments about C. Then we can now compute RA. So first, I have to present method of consistent deformations by selecting B as the reaction at B as the redundant force, and we remove it so that it will deflect freely as shown, and I apply double integration first. So I'll call this deflection delta B, which is expected negative. So I have to extend this loading and counter it upward, and the distance from this section to A is X. By the way, summation moment C equals 0, so RA1 times 18 equals 36 times 4 plus 18 times 10. 5 plus 8 is 13, the moment arm. So that is X. Considering the entire system first, RA summation moment about C equals 0, so RA times 18 equals 36 times 4 plus 18 times 10, not yet extended. Then this is 5 plus 8, so 13. Solving for RA1 for determinate beam 138 kilonewtons. So we then section this part and set up the equation of the elastic curve, differential equation of the elastic curve. EI y double prime is equal to 138 times x plus 18 times quantity x minus 10 over 2, or 9 x minus 10 square, minus 18 times x over 2, or minus 9x square, then minus 36 times quantity x minus 14. So that's the equation of the elastic curve. Integrating once, so EI y prime equals 138 over 2, or 69x squared, plus 3 quantity x minus 10 cube minus 3x cube minus 18x minus 14 square plus c sub 1. So there is slope at A, so that's why there is c sub 1. There's no deflection at A, so there is no c sub 2. Integrating again, EIY equals 23x cubed plus 0.75x minus 10 to the fourth minus 0.75x to the fourth minus 6 quantity x minus 14 cubed plus c sub 1x. Then we can now evaluate c sub 1 by setting x equals 18, y is 0 at c. So 0 equals 23 times 18 cubed plus 0.75 times 8 to the fourth minus 0.75 times 18 to the fourth minus 6 times 4 cubed plus c sub 1 times 18. So solving for C sub 1 is negative 9682 over 3. When if we divide this by EI, that's the slope at A. So knowing C sub 1, we can now compute the deflection at B by setting x equals 10 into this equation here. So negative values in the parentheses will be ignored. So EI delta B equals 23 times 10 cubed. So this is 0 minus 0.75 times 10 to the fourth negative. So ignore, then plus C sub 1, which is negative 9682 times 10. 9682 over 3 times 10. So delta B is equal to negative 50,320 over 3 EI. Then for the second part, we apply a unit upward load of 1 kilonewtons. So solving for the reaction here, reaction which is downward times 18 equals 1 times 8. So 8 over 18 is 4 over 9. And the corresponding deflection is FBB. We call this flexibility coefficient. So this is 4 over 9, so this must be 5 over 9. So we then section this part and call that X. Then set up the differential equation of the elastic curve for due to this unit upward load. So EIY double prime is equal to 1 times quantity X minus 10, then minus 4 over 9 times X. Integrating, EIY prime equals 1 half quantity X minus 10 square minus 2 over 9 X square plus C sub 3. So I'll use C sub 3 for this because this is a different beam, different loading. Then integrating again, EIY equals 16 x minus 10 cube minus 2 over 27 x cube plus C sub 3x. There is no C sub 4 again because when x is 0 at A, y is 0 also. So setting x equals 18, when x is 18 at C, y is 0 to evaluate C sub 3. So 0 equals 1/6 of 8 cube minus 2 over 27, 18 cube plus C sub 3 times 18. Solving for C sub 3 is equal to 520 over 27. And from there, we can solve FBB, setting x equals 10. EI FBB equals negative 2 over 27, 10 cube, plus 520 over 27 times 10, C sub 3 times 10. So FBB is equal to 3,200 over 27 EI. Then substitute into the equation, FBB times RB plus delta B must be equal to 0. So FBB times RB is the deflection, upward deflection, which should be equal to, numerically, to delta B, so that the final deflection at B would be 0. So that's this. So 3,200 over 27 EI RB plus negative 50,320 over 3 EI equals 0. So we can cancel EI and solve for RB. RB is equal to 141.525 kilonewtons. Then considering the entire system, summation moment about C to solve for RA because it is RA that is required here. So that is RA, RB, then R sub C. AX is 0, that's why the reaction at A is just RA or equal to AY. So summation moment about C equals 0. So R sub A times 18 plus RB 141.525 times 8 equals 36 times 4 plus 18 times 10 times 13. 5 plus 8 is 13. So we can now compute RA. And RA is equal to 75.10 kilonewtons. So that's it for this problem. And I'll give you a problem for you to uh, solve also. And I want you to apply the same approach and verify the result on the next slide. So for your exercise and to verify if you have understood the preceding examples, then this is your part. I want you to solve for reaction at A. And the answer is equal to 125 over 18 kilonewtons exactly, and approximately it is 6.944 kilonewtons.